Hi Math 250B students. It's the weekend and I haven't gotten to talk about math for a few days, so I thought I would check in with you here. Hope that everything's going well with the homework and studying for the upcoming midterm. I promised that I would give you a little bit of extra help with some of this material towards the end of what I'm asking you to learn for the midterm in case you wanted to get an early start on it. I am going to go over all of this in class on Monday. But this is just for those of you who have some time on the weekend, and I know several of you have already pretty much finished the review packet and some of those materials, so I want to give you some more things to chew on if you're looking for that. So there are basically a couple of concepts in section 5.3 that I would like to go over with you real briefly. Okay, I'll try to keep this short. I know that your time is valuable, but hopefully this will be helpful to you as you're kind of getting into chapter 5 and what's going on. So just to set the stage for this again, I'll remind you that we are talking about linear transformations, and these are functions. I'm going to draw my picture over here. These are functions which we denote with T, that goes from one vector space to another vector space. Okay, and the other thing is that the functions have to respect addition and scalar multiplication. So that's all in section 5.1 of the book, and I did talk about it in class last week, so you should have that in your notes. Okay, but it's really just a function in the same way that you can talk about calculus functions going from the real numbers to the real numbers. The only difference here is we can go from one abstract vector space to another and talk about a transformation between them. I kind of like to visualize this a little bit. I didn't draw this picture before. I kind of just draw a couple of circles to kind of represent the vector spaces themselves. And so there's a vector space V, and I also like to draw the zero vector. And I distinguish the zero vector from V from the zero vector for W like this. Okay, so these two circles really represent the vectors from these two vector spaces. And remember, the two vector spaces could be very different. V could consist of polynomials and W could consist of calculus functions. Or V could consist of traditional vectors in Rn, and W could consist of matrices. Right? There are lots of different combinations here. But one thing that we talked about that any linear transformation must do is it must send the zero vector to the zero vector. So this is a quick test if you're asking whether or not a particular transformation T is linear. This has to be true. Okay, so you can plug in whatever the zero vector is, whether that's a zero matrix or a zero polynomial or a zero traditional vector, whatever it is. If you plug it into whatever the formula is for T, you have to get the zero vector out. And if you don't, then you can stop. You don't have a transformation. Okay, but anyway, this is just a function. So you have inputs on the left side, call that V, and it just maps over here through this function by some formula to T of V. So we kind of have arrows kind of going across from one side to the other. Okay? And T has to respect addition and scalar multiplication. All right? Now, it turns out that we can relate this idea of this transformation back to something we talked about in the last chapter. Namely, there are a couple of subspaces that I would like to introduce to you, and these are the topic of section 5.3. So the first one is the so-called kernel of T. Okay, the kernel of T. And what this is this is going to be the set of vectors little v in capital V such that T of V is 0. And of course that's the zero vector of W coming out on the output side. So what is this talking about? What we're looking at here is a set of vectors in V that the transformation maps to 0. So there's certainly a possibility that a lot of vectors here from the vector space V could end up getting sent over here to the 0 vector of W. Okay, so you can look at all of those vectors, whichever ones they are, and it forms this set right here. Okay? And that is, in terms of the visual picture, that is the kernel of T. The kernel of T is those vectors that, basically the way I like to say it is those are the vectors that get killed by T. T transforms them to 0. Okay? And it turns out, and I'm going to show you this as a very easy little exercise on Monday, but this kernel of T turns out to be a subspace of V. So it's not just a subset of V. Obviously you can see it sitting inside of V here. But it is actually a subspace, which, as you know, means that it is closed under addition and scalar multiplication. Okay? So maybe I can write down a couple examples just to kind of give you the idea of what's going on here. So here's an example, maybe. Let's say we take T to go from, oh, I don't know, how about R3 mapping to M2 of R. So this is V and this is W. And my function is just going to be T of ABC equals, I have to give you a 2 by 2 matrix as an output. Alright, let's say I take 0 and A minus B plus C and minus A plus B minus C and 0. Okay? So I input a 3 tuple in my vector space V and I output these 2 by 2 matrices right here. So, first of all, I'm going to have you take my word for it for now that this really is linear. That would be worth practicing to check that it does indeed respect addition and scalar multiplication. So you could do that, and I'm going to not do that just for the sake of keeping this little video relatively short. But what I want to do instead is focus on trying to find the kernel of this transformation. Okay, so the kernel, let's remember what it is again. It's the inputs. It's the inputs from V. So it's a subset of R3 actually. We're focusing on the R3 side. It's the vectors in R3 that get killed by the transformation. So it turns out that the way that you go about trying to find the kernel, so let's ask that question, what is the kernel of T? The way that you go about addressing that question is you imagine that you've transformed some vector ABC into this and that it has become the 0 vector. In this case, the 2 by 2 0 matrix. So what you do is you set T of, well, in general you set T of V equal to 0. In this case that means you set T of ABC equal to 0, 0, 0, 0. Which of course is just, this is the formula right here for T of ABC, so I can just go ahead and put that in here. So you actually create an equation here. Okay, all 4 entries of this matrix have to be 0. Well, if you look at that, that's really saying that A minus B plus C is 0, and negative A plus B minus C is 0. It's a system of equations, which by now we're pretty good at solving. It turns out the second equation is actually just the negative of the first equation, so it doesn't really tell us anything that we can't just get from the first equation. And if we look at the first equation, of course, we're really just solving a little system. Okay, this is just a little system of equations. The A is the leading variable, but B and C are free. So I could write C as T, and I could write B as R. Okay, so we've done this before, right? And then A would just be R minus T. So the kernel of T, we've already found it actually. The kernel of T is, it's the set of A, B, and C, but I'm writing them now using the variables R and T. So this is such that R and T are real numbers. Okay? So there is the kernel. By the way, remember I said it's a subspace of V. So that means it has a basis and it has a dimension. And so if I asked you for a basis for this, of course you guys have already known how to do that. You basically just take this vector and you bust out the variables. right? So you could bust this out. If you bust out the r, you'll get 1, 1, 0. And if you bust out the t, you'll get negative 1, 0, 1. So everything in the kernel of T is basically a linear combination of these two vectors. And so we can actually not only find the kernel of T, we can find a basis for it relatively easily here. Okay? So, and then the dimension, right? The kernel is two-dimensional. So in some ways, it's not any different than the kinds of stuff that you've actually done before. It's just it's being expressed in some slightly different terminology. Okay, let's try another example just to practice this a little bit more. Let's suppose we take T to go from let's take P2 of R to if I want to use polynomials, I guess. Let's map it to, well, M2 of R is fine. I can use this one again. Via, so this time I'm going to take T of AX squared plus BX plus C. That's my input. And I'm going to map it to a 2 by 2 matrix. Let's say I go to negative 2A plus C. And here I go to B plus C. And here I go to negative 3 minus 3c. And here I go to, oh, I don't know, how about 6a minus 3c, something like that. Okay? Again, take my word for it that this is actually linear. Okay, this respects addition and scalar multiplication. But let's ask the same kind of question. Find a basis for the kernel of T. Okay, so again, the basic idea here is we want to solve for a, b, and c, but this time they are expressed in a polynomial, right? Not a 3-tuple. It's a little bit different. You'll see when I write down the answer in a minute. But anyway, the basic idea is we're just going to set T of ax squared plus bx plus c equal to the 0 vector, which again is just all 0, right? And so that just means that all 4 of these entries have to be 0. So we get minus 2a plus c is 0. We get b plus c is 0. We get negative 3b minus 3c is 0. And we get 6a minus 3c is 0. Okay? That's just a system of equations. Here, let me give myself a little bit more room here. That's just a system of equations that we can solve. We're looking for the kernel of this transformation. It's going to be a subspace of P2 of R. Okay? So we just get a little matrix system. Oops, there's actually 3 columns because I have 3 unknowns, which are A, B, and C. Okay. I have 0, 1, 1, 0. I have 0, negative 3, negative 3, 0. And then I have 6, 0, and negative 3. What you'll notice is that the third and fourth rows are just multiples of the first 2 rows. So in this case, we're going to end up with 2 pivots. Notice how I'm not really row reducing the matrix completely. I'm just getting it into enough of a form that I know where the pivots are. But I can see, for example, that my C is my only free variable. That's the 3rd column, right? So the C variable is free. B is equal to negative t, just based on the 2nd line. And then A is going to equal, what is it, 1/2 of t? Yeah, I think so. All right. Now we have to be a little careful this time. I don't want to write this as a 3-tuple. Rather, what I want to do is I want to write my kernel of T. I'm going to put in the A, B, and C, but I'm going to put them into the polynomial, right? This time I have a quadratic polynomial. So it should be 1/2 t x squared minus tx plus t. So it's the set of all of those expressions where t is my free variable, so it's any real number. See how I wrote that? And if I want a basis for the kernel, to get a basis, I just bust out my variables, just like I did on the last example. This time I only have one variable to bust out, which is the t. Once I take it out and factor it out, my basis is just this polynomial. Okay. Notice that when you write down the basis, you shouldn't be seeing any of the free variables in that basis. It's just the actual polynomial itself. So in this example, the kernel is only one-dimensional. Okay, so it's just a one-dimensional kernel. Okay, maybe just one more example to really make sure. Actually, a couple more examples maybe. Just do a couple more things here. The third example, let's do T from P3 of R to P2 of R via, okay, I'm going to do this a little differently. I'm going to write my polynomial this time just abstractly as P of x. And I'm going to map it to the, let's take the second derivative of P of x minus 3 times the first derivative of P of x. I'm just making this up. Okay. So trust me once more that this really is linear. It'd be a very good exercise for you to just practice that that really is a linear transformation. Okay? But let's see if we can find what the kernel of it is. Now, in this case, the problem, this is a little bit harder because I didn't write out the polynomial in terms of powers of x. I wrote it kind of in this very simple abstract form. This simple abstract form actually is an advantage when you're showing that t is linear. Because, for example, you don't have to deal with, like, you know, having two polynomials of the form ax cubed plus bx squared plus cx plus d. That gets rather cumbersome to write all of that out. But here you can just write out p of x and q of x. Right? Very simple abstract way of writing your polynomials. So that actually is an advantage of this compact p of x notation. But once I want to start to figure out what my kernel is, it's going to be important that we, so let's just write down the question here. It's going to be important for the kernel of t that we actually rewrite p of x. So I'm going to start it off that way. I'm going to rewrite p of x. It wasn't given to me this way, but I know that I am inputting a polynomial of degree 3 or less, so it has to have this kind of form. Okay? So then we can figure out, okay, so then let's just find these two derivatives and figure out what the transformation formula actually is. So p prime of x, for example, we just take the derivative of the p of x, so we get 3ax squared plus 2bx plus c. And then we also want to take p double prime of x, which would be 6ax plus 2b. Okay? So now I've calculated the derivatives that I need, and I can evaluate my transformation. So t of p of x, then, is going to be the second derivative minus 3 times the first derivative. So the second derivative is 6ax plus 2b, and then minus 3 times the quantity, 3ax squared plus 2bx plus c. That can actually be simplified pretty nicely. So this is going to be the x squared term. The way you want to simplify polynomials is according to the powers of x that you have. So negative 9ax squared. And then my x term is, I've got 6ax here, and then minus 6bx. So 6a minus 6b times x, right? And then my constant term, let's see, I've got 2b right here, and then I've got minus 3c for the constant term on this side. Okay? So this time my output is a polynomial, and I still want to find the kernel of this transformation. Okay. So you see the difference here? This time we actually had to do a little bit more work on this example. The polynomial was written in an abstract form, and it became necessary for us to rewrite it using the variables and take these appropriate derivatives. Okay? So we can ultimately derive a nice formula for the transformation, but we had to do this work to really come up with it. And that is something that does arise sometimes. Okay? So this is my formula. Now I'm ready to go about finding the kernel. Okay? To do that, as usual, we set the transformation of the vector v to 0. And in this case, the 0 vector is actually just the polynomial 0. Okay? It's just the polynomial 0. So we have a familiar situation where we have an expression for a polynomial equal to 0. The only way that can happen is if all of the coefficients are 0. So the x squared coefficient has to be 0, the x coefficient has to be 0, and the constant coefficient has to be 0. All three of these equations. I think what I'm going to do, instead of putting it into a matrix, we could of course put this into a matrix and solve it as a system, but you can clearly see from the first equation that A has to be 0. Then plugging that into the second equation, B has to be 0. And plugging that into the third equation, C has to be 0. So A, B, and C are all 0. And the only variable that is not constrained is D. There is a D up here, and remember, this is the domain. This is the vector in V that we have to look at. So D is actually free. Okay? And so your kernel then, the kernel of T, is just the set of all of these constant polynomials. So T is just some fixed real number. So you're just looking at all the constants. Makes sense. I think you guys would all agree that if you plug in a constant into this transformation and you do the right-hand side to evaluate it, that constant is going to be transformed to 0. It's going to be killed by this transformation because this transformation is taking derivatives. Okay? So this is my kernel, and my basis in this case, my basis would just be the set of 1. Okay? One final example on the kernel, and this is one that's based on something that I did in class last week. Remember that if I fix an m by n matrix, then we can actually define a transformation T from Rn to Rm via T of x, and I want you to think of x as a column vector with n slots, equals A times x. Okay, so basically you take an m by n matrix, you put a column vector with n slots next to it, and you can do that multiplication and get a vector with m slots as an output. Okay? So here's a good question to think about. In this context of this type of example, what is the kernel of T? The kernel of T, that's the set of vectors x that get transformed to 0. In other words, we would be, to find the kernel of T, we would be setting this equal to the 0 vector of Rm, whatever m is. So it's really this equation, which actually should look very, very familiar to us, right? That looks like a linear system. It's a linear system, and in fact, the x's that satisfy that linear system, they comprise a very special subspace of Rn. If you remember what it's called? It's the null space of A. Okay? So if I ask you to find the kernel of a transformation that is of this type right here, from Rn to Rm via this matrix, I'm not asking you to do anything new that you haven't done before in the previous chapter. You simply find the null space of the matrix. Okay? Does that make sense, I hope? So that's just my crash course on the kernel of a transformation. It's just telling you which vectors are killed by the transformation capital T. It depends on the problem, of course, and you have to solve something usually to come up with it, but you're solving equations in the same way that you've been solving them all semester, so there's nothing really that new about that. Okay? Having said that, I'm going to pause the video and start a new segment to talk about the range of T, which is another subspace. But the range of T is actually a subspace of W, so it's a little bit different. So I will attach a separate video to talk about that so that I don't make these videos too long. Okay? Thanks for watching. Let me know if there's questions about this. The next time you see me, feel free to to catch me and let me know if there's any issues. I hope some of these examples have been helpful. Okay. Oh, by the way, there's some recommended problems from section 5.3. You can take a look at those and try and practice them. It'll be a lot of the same kinds of things that I was just showing you here. So, okay, great, thanks.